coloring a graph is to color every vertices of a graph so that any two adjacent vertices does not share the same color. For example, this graph is not a coloring because these two adjacent vertices share the same color. However, this graph is a coloring because any two adjacent vertices does not share the same color. And this is one of the most basic problems in graph theory. For finding minimum number of colors for a planar graph, there is a famous theorem called four-color theorem, and this was proved by a computer. But in 1879, it was still to be proved by Alfred Kemp. The four-color theorem states that every planar graph can be colored by at most four colors. But his proof was wrong, and it was proved to be wrong by Percy Hill in 1890. And while he was disproving this, he proved that there are at most 5 colors to color a planar graph, and that's called five-color theorem. And he used this Euler characteristics to prove that. And in this video, we'll take a more generalized topic called list coloring. In terms of list coloring, we can show that every planar graph is 5 choosable, not 5 colorable, which is indeed a more stronger statement than 5 colorable. We will soon figure out what this means and show it a proof for 5 choosability. Thanks.
Now I will introduce the list coloring and k-choosable. First, consider the graph G which has n vertices. The list coloring on G is the coloring on more restricted condition. First, color the adjacent vertices with different colors. This is same as the usual color, but next, there is a restriction on possible colors on each VIs. This is the difference between the list coloring and usual color. We set the list of the possible colors to each VI. We define LVI be the set of all possible colors on VI. If the LVIs are same, then this is the usual coloring, since it is K coloring where the cardinality of LVI is K. Now we can define the K choosability by from list coloring. We say G is K choosable if the list coloring is possible for all possible lists LVI for I equal 1 to n, where LVI, cardinality of LVI is bigger than or equal to K. Obviously, K choosable implies K colorable, since if the graph G is K choosable, then for all lists such that cardinality of LVI is bigger than or equal to K, then the list coloring is possible. So we can set the LVIs are all same and the cardinality of LVI equal to K. Then this is K coloring, and this is possible by K choosability of G. So G is K colorable. So K choosable is more strong condition than K colorable.
From now on, we will prove that every planar graph is 5 choosable, which the proof is due to Thomason in 1994. As said earlier, if every planar graph is 5 choosable, then it implies that every planar graph is 5 colorable. So this is another proof of 5-color theorem. However, it is known that every planar graph is not 4 choosable. So there exists a planar graph that is not an list that is not 4 choosable. So this is the strongest we can get. For proving this, we are using a trick. We are using a trick and an induction. Trick for induction. So we'll make a proposition that for every nearly triangulated planar graph G and a list with outer face K is V1, V2, and Vk. So this is in the cyclic order. And we also assume that the vertices of the graph is at least 3. Then if the V1 and V2 is properly colored, so they are adjacent, so their color will be obviously different. and for every vertex in an outer phase, but not V1 and V2. V1 and V2. So for every vertex in K, but not in V1 and V2, but not V1 and V2, their list size are at least 3. And for every vertex that is not in an outer phase, the size of the list is at least 5. Then the graph is choosable. Then the graph is choosable according to that list. So this is actually a strengthened version of a theorem. So we can assume that the graph is nearly triangulated because for the definition of nearly triangulated, we say the graph is nearly triangulated if every inner face is a triangle. This condition can be added if we triangulate every inner face of the graph, of the planar graph by just picking some vertex and adding an edge to other graphs. So if we find the coloring that works on another graph which have edges added, then it obviously works on the original graph. So we can assume that the graph is nearly triangulated. And for others, we assume a stronger statement. So we assume that the list size is at least 5, but for this one we assume the list size is at least 3. So this is a stronger statement. It tells more. And we assume also V1 and V2 is correct. Then this is a stronger statement. So if with those propositions we can easily prove the theorem because for V1 and V2 we just set the colors arbitrarily, and for other vertices this all of this just works. So we can just use the theorem to prove it. So the reason why we are strengthening the claim is because we are using the induction. So in induction we have inductive hypothesis, and from that inductive hypothesis we are growing the proof to the larger case. So if the proposition is stronger, then we can use the stronger induction hypothesis. Thus it may be easier to prove the original statement. From now on, we will prove that every planar graph is 5 choosable. This proof is due to Thomassen in 1994. Note, as we said earlier, that if every planar graph is 5 choosable, then it implies that every planar graph is 5 colorable. Then one might wonder that is every planar graph 4 choosable, because we know every planar graph is 4 colorable, but it is not. There is a counterexample for that. So this is the strongest we can get, that every planar graph is 5 choosable, and we will talk about the proof. For convenience, we will assume that the planar graph G is nearly triangulated. By saying nearly triangulated, it means that every inner face of the planar graph is a triangle. It doesn't care about the outer face, but it cares about the inner face. Every inner face is every inner face is a triangle. So if every nearly triangulated planar graph is 5 choosable, then obviously every planar graph is 5 choosable. This is because if the inner face is not a triangle, then we can just simply add an edges with a center. So in a center we just add all edges that are not adjacent to such. Then every face becomes a triangle. So we will just assume that every planar. So we are just assuming that the planar graph is nearly triangulated, and we obviously have a list, and we have an outer face. And we assume that the graph has at least 3 vertices because if the graph has 1 or 2 vertices, then the theorem can be easily proved. So we can assume that it has at least 3 vertices. And in this proof, we have a trick that we actually strengthen the claim. We make a harder version, and we use induction. Then people might wonder why we should strengthen the claim, because it's like quite nonsense, because we don't have to solve the harder problem. But the point is, we are using the induction, and for induction we have the induction hypothesis. We have the induction hypothesis, and we are growing it to make the larger version, to to make the proof grow, to make the proof with an added vertices or edges or whatever. So if the induction hypothesis is strong, as we strengthen the claim, then we are assuming a stronger version. Thus maybe it might be easier to prove a stronger statement. So it depends, and Thomason is using this trick to prove that every planar graph is 5-choosable. So the claim with strengthening is this: if the vertex v1 and v2, this is in the outer phase, so this is in the cyclic order. So basically v1 and v2 is of two vertex that is adjacent in the outer phase. So they are colored, and for every vertex that is in the outer phase but not v1 and v2, then their list is at least size 3. But we have a list of size 5, so this is more than enough. So also for every vertex that is not in the outer phase, the size of list is at least 5. So this is the same as the original one. Then we can show that G is choosable, and we will soon show this by induction. So we'll prove this by using an induction. So for induction, we are using an induction on the number of vertices. Then the base case will be the number of vertices equal to 3. Then this case is actually easy because v1 and v2 is colored. And for the rest of the vertices which is not colored, then we can just assign the remaining vertices, the remaining one in the list, because the list is at least size 3, so we just have a remaining color and we can just assign it. So the base case is easy. So we will continue. So for the inductive case, we will assume that the number of vertices is at least 4, and we have two cases. For case 1, the graph has a chord. By meaning a chord, it means there is an edge that connects two vertices in the outer face which is not adjacent. So this means there is an edge that connects two vertices in the outer face, but it's not on adjacent vertices. So this one is not a chord because it connects because it connects the vertices that's in the outer face, but they are adjacent. So this is not a chord, but this is a chord because there will be a vertices. So we are assuming there is a vertices. So these two vertices are not adjacent. Then we can prove this. So let K1 be the side that so we have the inner face demarcated as two sides. One is K1, one is K2, and we, without loss of generality, we assume that K1 is a part that contains V1 and V2. So then we will use induction on K1 and then use the induction on K2. So we will start for K1. For V1 and V2 is colored, and for every vertices in the adjacent in the outer face, they have at least three colors in the list. And for other vertices, there is at least 5 colors in the list. So we can color this one because the number of vertices is strictly smaller. So we can color this one by inductive hypothesis. And then we have a coloring here. And these two vertices are colored. In a K2's perspective, this one can act as a V1 and V2. This one can act as a V1 and V2. So they are now colored, and these things just remain same. So for other ones, their size is at least 3, and the inner one, their size is at least 5. Then we can also use inductive hypothesis here because their number of vertices are strictly smaller. And in any cases, we didn't violate anything about the nearly triangulated one. So we can again apply the inductive hypothesis, and then we complete the proof. So now we will talk about case 2, where G has no chords. Then we will think about the V3. Which one's V3? Then we think about its outer face. We define the outer face K as V1, V2, and V3, and whatever as the cyclic order of the outer face. and as the number of vertices is at least 3, then the number of vertices in the outer face is also at least 3. So we have colors in V1 and we have colors in V2 and we have V3 which is not colored and which have a list of size at least 3. So now we will think about it. So for one point, that every vertex that is adjacent to V3 is not in the chord, is not in the outer face. This is because the G has no chord. If one of the vertices that is adjacent in the adjacent to V3 and not V2 or V4, and for the record, we assume that V4 is different to V1. We can also think that V4 is V1, that the outer face is a triangle, but it works as it works in a totally same way. So we will just omit it and we will just assume that the outer face has size at least 4. So okay, so we have V2 and V4 and another number vertices that are adjacent, and they are all not in the outer face because otherwise then we find a chord, and this is a contradiction to the assumption. So they are not in the outer face, so they properly define the faces, and as we assume that the graph is nearly triangulated, so every vertex that is adjacent to V3 is adjacent in their own way. So V2 is adjacent to W1, W1 is adjacent to W2, W2 is adjacent to W3, and W3 is adjacent to V4. Then if we remove V3, then they will form a proper nearly triangulated planar graph. So we will do like this. So first we will think about this. LV3 has at least 3 elements, 3 colors. And we can exclude V, and we have to exclude V because V2 has already colors B, so beta. So we'll remove the color beta from the list LV3. Then we have P and Q and maybe another colors or maybe no colors, but we are sure that we have at least 2 colors. So we will just pick that 2 colors. We will say that is P and Q. And as we said that all vertices W are not in the outer face, so their lists are at least size 5. Then it's safe to assume, then it's safe to just remove those 2 colors P and Q from those lists. So for list W1, W2, W3, then we will remove the color P and Q. Then their size will possibly decrease to at least 2 colors. So their size will now be greater than or equal to 3. So now let's see what happened. So V1 and V2 has a color, and for all vertices that is in the outer face. So by outer face we don't mean V3 but this outer face. In this outer face they have a list of color at size 3, and for the original outer face vertices they also have list of size at least 3. And for the inner face, we didn't touch anything, so they will obviously remain on list of size 5. Then we can just use inductive hypothesis to color these faces. Then now we are sure that W1 and W2 and W3 and all vertices with W have no color of P and Q because we removed that from the candidate of possible colors. So they are not possible to be colored as P and Q. Then the possible color for V3 is P and Q, and they don't share these colors. And V2 have color beta, which is different from P and Q. And now we have 2 cases. First case, V4 have color P, then we can just color Q. Otherwise, we can just color P. Then we find the color for V3, and the proof is complete. We found all cases. Thus, every planar graph is 5 choosable.